Welcome to a demo of the WoundSim Abaqus plugin. Um, now, WoundSim is a product that currently is used to develop finite element models of composite overwrapped pressure vessels, COPVs. Uh, now, now it has WoundSim has two pieces. It has what we call a WoundSim GUI that's a standalone piece of software that we can draw the COPV layup, um, manage the creation of a finite element model with some kind of default controls, and then actually manage the running and post-processing of the job separately from outside of the FEA solver. Now, internal to the FEA solver, which in this case we use Abaqus, we actually create a model of the COPV right there inside of Abaqus, and we generate all the geometry and the mesh and do all the material calculations and all of that inside of Abaqus CAE, and we store all that information on there. So we have two ways of doing it. So we can build the model in the WoundSim GUI, which is going to be the future home of software to wind the COPVs, or we can do it just inside the FEA solvers. So this demo is going to show the process of building everything within the Abaqus CAE plugin. All right, so typically the way we'll start is the user will define the geometry of the liner. That's not what WoundSim does. It's done outside of the WoundSim tool. So that geometry might be created in SolidWorks or CATIA, or right there inside of Abaqus CAE. So in this case, I've kind of created a dummy liner. It's kind of a uniform thickness, not a very realistic liner, but just a simple symmetric liner to make it easy for a demo. What I'm going to work on for the demo is actually a symmetric liner, which means we have a tank that is exactly the same on the top and bottom. Maybe not a common occurrence, but it makes it easy for demo purposes, so we don't have to jump back and forth from the top to the bottom. All right, so let's say you're in the Abaqus CAE and you've created your geometry. You have to mesh it up, and then we're going to use that as a basis of determining what the COPV geometry will look like, the layer geometry. All right, so to start this, first we got to create our XML. This is going to be our output database in WoundSim. So I'm going to create it. We'll call it demo XML, which is our model name here. And then what I'm going to do is we store all the information for the materials on our XML file so that the WoundSim GUI has access to it, as well as the Abaqus GUI. So even though we may have those materials built inside of Abaqus already, we need to store them into the XML file. So we have this. The very first step here is generating the materials. Now in Abaqus, we've already got these materials. We've got aluminum for the liner, T700, T1000, whichever one we want to use. So what I'm going to do is I'm just going to say import, and what we're going to do is import from Abaqus. Now I could have my own XML library. This is just a library in WoundSim format that stores all of the either material data or mandrel data. So in this case, we're just going to import our geometry or our materials from within Abaqus, and we see we've got all of this stored on here now. So for example, T1000 here, here's our elastic properties. We've got expansion properties, conductivity, specific heat, fiber, no fiber matrix properties, but we got failure measures also. Alright, so the next thing we got to do is define the outer perimeter of our liner so that when we start adding layers to our COPV, we know exactly what the underlying geometry looks like, and we know what the shapes of the layers will end up being. So we've got to create a mandrel. So in this way, let's call it mandrel 1. This is half a tank, a symmetric tank. We have different ways of defining the liner. Usually it's a liner profile, which is an existing liner geometry that you're going to use. But we can do ellipticals. These are more analytic things, elliptical, geodesic, or from a CSV file. Maybe you have some CAD program that outputs XY data. You can import that. So what we're going to do is we're just going to select a set that defines the outside perimeter. So I'm going to highlight it. So we're going to look through these sets and we see that one has the outside perimeter. Alright, then I'm going to hit this that just says compute the coordinates, and then there's all of our points that we're going to use to define the liner. And then we have these tools up here to thin those points out. Right now we have 88 points up here. That's reasonable. We probably can survive with that. But if we want to really speed things up a little bit, we can coarsen that up just a little bit. And you see it doesn't coarsen up in here because we have some variation in the orientation from element to element. So the algorithm just keeps all those points. Alright, so that's going to be our outer profile. That's our mandrel, we call it, our shape of our mandrel. Alright, now I'm going to create the model. Now, we have an Abaqus model, but we don't have the model that's going to be stored on the XML file yet. So we have to create that. So here's the existing Abaqus model. So I'm just going to hit this, so we'll name it demo, same as the Abaqus model. Alright. Alright, and then we have two things. We have the results and we have the model. So first we've got to build the model here. So I'm going to create a COPV. And you'll see this is a repository of multiple COPVs. So if we want, we can, let's say, do a model of 2 tanks and a missile or something. You know, we have the oxidizer and the fuel tank all in a single model, so we have 2 COPV models. But in this case, we're just going to build a single model. So we have we just have the one liner, the one mandrel. We're going to do continuum geometry. We could do shell, but we'll stick with continuum. Alright, so for the COPV, we have to generate the layup, and then we have to mesh it. And then these other icons are building the rest of the model, putting the COPV into an assembly, generating the material properties, generating the loads, and then finally running the model and post-processing it. So we'll start with the layup. So we have an empty slate here. We've got a whole bunch of stuff here. So let's just kind of walk through one layer at a time and see what it all means. So first we'll just add a layer. So default layer is a geodesic helical. So this means we have a helical that if you're given an angle, like let's say 10 degrees, the code will compute exactly where it terminates. So it starts out in the cylinder at 10 degrees and then it gets close to the polar bus. Alright, so we're going to enter this position by angle. Let's just say 15 degrees. So you'll notice this tool up here just is a symmetry constraint. Well, we've got a symmetry constraint because we're only dealing with half a tank. We have some things up here if we want to turn off some of the columns because there's a lot of stuff to display. But alright, so I'm going to select the material. We'll just do T1000. This is in millimeters, so say a bandwidth of 10. I'm going to put a full millimeter. Usually it's a little bit thicker than that, but I want to make it easy to view. Alright, so we'll do a rounded end cap. And we'll see what this end cap factor is. I'll just stick with 1, but we'll need to change that. Alright, so notice this is the bottom of the layer, so the bottom of the tank, but that's all grayed out because since the tank's symmetric, we don't have to fill that all out. So what we could do is just turn that off entirely. Alright, and just hide it. Okay, so I've got my first layer here. I'm going to go ahead and sketch it. So let's kind of display it like this so we can see both. Alright, so we see this kind of a bulge here, so we're terminating a layer all the way up near where the fillet radius is. So really, usually these layers are slipping around a little bit, so they kind of flatten out. But so we could do this a couple of ways. So let's just, the first thing, let's just try changing the end cap factor. And what this is it just says if we look at the way this is drawn, we have an analytic expression for the thickness buildup. And then at some point it has to terminate and drop down to the end of the layer at 0. So the question is, where does this occur? So the default is we have a bandwidth times an end cap factor. that distance is 10 times 1. So if we march from here where it intersects the liner, 10 units will end up somewhere around here, and then we draw this line to figure out where it tapers off. So let's just say we want to flatten that out. So we can kind of flatten it out a bit. We could do that even more. Or what we could do is, instead, we know that these things kind of flatten out naturally as we get to the polar boss because they're kind of being pulled around the polar boss. So we can terminate it a different way. We can say by to boss. Now you'll notice this all of a sudden just says, oh, we don't have a wind angle. We'll calculate exactly where the wind angle is when it hits the boss. Alright, so let's resketch that. Now what I'm going to do is I'm going to draw this as straight. Well, first we'll start with rounded, and I'll show you why I typically switch this over to straight. So this is pretty straight as it is, so we have this thickness kind of building up. So typically what I do when we go to the boss is I'll flatten that out a little bit. Alright, so there's a layer that runs all the way up to the boss. Now when we say to boss, we have some equations that approximate how thick this buildup is going to be. Now once we go to, let's say, 10 or 20 layers, we may start to vary from what actually occurs right at the polar boss. So we've made it very easy for you to tweak that, and I'll do that at the end. Alright, so what we're going to do next is add a hoop. So hoops typically end a different way, and that's by coordinate. So if we look at this, this is it's displayed as our x coordinate, but I've got it displayed vertically. But so this distance somewhere around, measured from the center of the tank, somewhere around 70. Alright, so it's got a distance of 70 from the center. Wind angles typically 90 or 89, something like that. One thing I forgot to mention is the to boss. We calculated exactly where it terminates up here, and based on this cylinder radius, the wind angle that would cause it to terminate exactly there is 13.3. So we fill that in when we're done. Alright, so the next thing here, we got a straight. I like to use rounded, and make this hoops, since they don't build up in thickness, they're usually pretty thin, and the default end cap is, again, bandwidth times end factor, so that becomes a very sharp sliver. And depending on how the wind is, what you've selected for, like the dwell, that may be sharp enough, maybe too sharp. So again, you have some controls to modify that. So what I'm going to do is set it to 0.75, and we'll just see what it looks like. Okay. So we see our hoop terminates at a position of 70. Alright, so let's add a couple more layers. I'm going to highlight both of them and hit plus, and then you'll see what it does is it just copies both of them control by control. So the first thing is, with geodesic, instead of going to boss, I'm going to just enter an angle. So what we'll do, this is the angle at the top of the tank. We'll say 20 degrees. Okay, and here I'm going to use rounded end cap factor. I'm going to do a little bit less than 1.5 because this is away from the polar boss, so it doesn't flatten out quite as much. Now with hoop, I'm going to use a different route here on this one. I'm going to say setback and 10 millimeters. What that means is it's going to set back from the previous hoop by 10 millimeters. So let's say I've got big long stack of hoops, and each of them sets back a little bit. So I may have 5 or 10 of them that set back from the first one, and then we start the process all over again. So by using setback, we really only have to change this, and then all the ones that are set back from it would get shifted around as we change that one number. All right. So let's see what we got here. So there's our next helical, and you can see this is set back to 60. Okay. Now we can taper this a little bit more. It really depends on kind of the friction of between the bands, so how much it starts to build up versus how much slippage there is. So for now we'll just assume that looks right. Alright, so what I'm going to do is do the same thing. We're going to highlight these two. Now instead of setting by angle, the helical by angle, I'm going to use the same process. I'm going to use the set back. Now this one's a little bit different. Instead of setting back from the end of the layer, we set back from where the end cap starts. So we'll set back a few millimeters from here. So let's just say 3 millimeters. Alright. And then the hoop, we're still going to use the same setback. So we're going to go from 70 to 60 to 50. Okay, so there's our next layer. And we see our hoop down at 50. Okay. Alright, so let's do the 2 boss again. And we want to reset that to, let's say, 70. So I'm going to highlight those two, copy them, and we've got the 70 distance that we want, and we got the 2 boss. So here we go back to 70, and we've got the next layer coming up to the boss. Okay, so then let's just, for sake, let's just do 2 more of these. Same thing. We'll really stack this up in the boss area. Okay, so now we've got we probably need another helical out here, but that's fine. So here I forgot to set this to set back, so let's do that. Okay, so that'll set back from the previous. Okay, so there's the one at 70, here's the setback another 10. Okay, now one thing you'll notice, I have this highlighted over here and this row gets highlighted. So if I'm in the sketch, all I have to do is move my cursor over and it'll highlight the row that I'm at. Alright, likewise if I'm fiddling around here, I can say highlight layers and it'll highlight the layer. Oops, I should highlight once I get my cursor over there, it'll highlight the layer that I've just asked it to highlight. Alright, so anytime you touch something or click on it, it'll re-highlight things. Alright, so let's say we're okay with this, except we've wound the tank and what we found is that this thickness is a little bit off. Let's say by 10%. That's a lot, but let's just say we're off by a bit. So what I can do here is, just to make it easy, imagine if we had 50 or 100 layers. I'm going to sort by 2 boss and this forward boss factor. So all this is that we calculate a thickness based on some literature, and sometimes it's good, sometimes it's off a little bit, so sometimes we have to tweak it. So this boss factor lets us just scale that up or down. So what I'm going to do is set it to 0.8, or let's say 0.9. Alright, so it's at 10% off. Gotta resort this. Okay. Alright, and what we've done is we've just reduced the thickness here a bit. So we can take it up or down however is necessary. Alright. So let's say that we're happy with this layup. Okay, we've got everything that we need. We'll go ahead and build it. Alright, so there's our geometry. Alright, we haven't meshed it yet, but that's a start. So let's go to mesh. What I'm going to do is just auto mesh. We'll start off with just not even thinking. Let's just let the program do whatever it wants to do. Alright, so there's a decent mesh. Okay, now we get in here and we're like, eesh, that does not look good. Alright, so we need to babysit this a little bit. Alright, so let's turn this off, and you'll notice this dome aspect ratio. This is what's critical. We're setting it here at the very maximum, So the smaller this number is, the better mesh you're going to get into here. So I really don't like going all the way to 4. So based on the number of elements along the tank, this aspect ratio and based on the thicknesses ends up as 4. So let's set it to, let's say, 125, and let's see what it looks like. Okay, so here we look a little bit better. All right, still have a few weird things going on here. That's if you turn off this, we've got these end caps are defined with quad dominant, so they can have some triangles in here, but it usually only happens in these regions. Sometimes it'll happen some of the others, but it's usually in right at the ends of the layers. All right, so overall we're looking pretty good, but if you've ever plotted stresses, let's say along the cylinder and along the dome here, cylinder and the dome, what you'll see is you have lots of oscillations in here where these layers are terminating, and then you get down here and it's nice and smooth, but there is some transition area here. So what this algorithm is doing is we're setting it such that we ask for a certain number of partitions, and as soon as it finds a partition where there's no partitions like this inside of it, then it's going to mesh this with the coarse mesh. All right. So the thing is, right around this transition area, we still have some oscillation. So this area we may want to mesh with a finer mesh. So let's see how we do that. So the auto is what we've got it set to. So that's the one that says, well, as soon as we find one that doesn't have any partitions in here, we're going to go ahead and mesh that with the coarse mesh. So let's instead set it back by some distance. Now if we set it back by 0, that's the interface between the dome and the cylinder, and I think it's right here. And then if we set it to 1, this would be where it starts with the coarse mesh, or if we set it to 2, this would be the place, or 3, and so on. Now I can't remember if it's this point or this point, but what we'll do is we'll set it to 2 and see what happens here. Okay, so yeah, that gives me my finer mesh in here, and then by the time we get here, we're pretty well constant in our stresses and strains. All right, so we've got our geometry, we've got our mesh. Let's put it into the assembly. So I'm going to add the instance. So we have a part COPV type, COPV1. Let's call it COPV1. That'll be the instance name. Now, boundary conditions. Include boundary conditions on the symmetry planes. Now, we have another one if we want to include an extra boundary condition to prevent rigid body motion, but I've already got that on the liner, so I don't need that. And then I want to include interactions. So the interaction is between the composite and the liner. So how do they slide with respect to each other? Are they bonded? Whatever our assumption we're going to make. So we don't have anything, so I'm going to hit the plus sign. Alright, so we want to highlight the outer master surface. That's the liner. Alright, and then the inner surface, well, we're in the process of creating the assembly. So what we want is the COPV1, that's our instance, and we want the liner interface, but we're not able to highlight this yet because it hasn't been put into the assembly. So we just, for now, we just have to know that this is what we need. Alright. Okay, so for example, let's just say we went back there and wanted to edit this. Alright. Oops, I think I did that twice. Okay, so now I can highlight. That's the liner. There's the line. That's the liner interface. See, now that I've instanced it, now I can actually highlight it. Alright, so anyways, that's our assembly. Color things by part instance. There's our liner part instance, our composite. Alright, the next thing is the material bins. Now there's a big long discussion about what we're doing behind here. In fact, this is the most complex part of the whole WoundSim. But from the user perspective, all of this is meaning is that we have theoretically a continuous wind angle for every element. Every element's got its own unique wind angle. But that would mean we have to do material transformations for every single element, and it's just too expensive. So we got to group them together. So what we're going to do is we're going to start with, let's say our lowest wind angle is like 10 degrees down here. So we're going to group all of those into one material. And then from all the elements that go from 10 to 10.5, we're going to group those to one material. And then 10.5 to 11, and so on and so on. So we're going to end up with, half a degree, so we can break 0 to 90, so 170, 180 different materials. Now the next question, the next thing to say is, why do we need different materials? Well, we've entered a material. Why do we need to do anything with that material? Well, we've entered T1000, but that's the material that is in the fiber direction, and throughout here the fiber direction is out of plane. So we have to transform those coordinates into a global direction that is in this XY plane. So each element will have its own orientation here, but the materials will all be grouped based on that wind angle. Alright, so anyways, so this is going to compute all the transform materials, generate the materials, and then generate the section assignments. Okay, so if I were to display this, then we would have all of this. Okay, so this kind of tells you how the wind angle changes. So down here, like in the brown colors here, these are the hoops that are a constant wind angle. They're about 90 or 89, whatever. But now this one, I think our first one was 10 degrees or 13 degrees. So this one would be 13 degrees. This one would be 13.5, this color. You'll notice it changes very slowly, 13.5 to 13 to 12.5. And then as it comes around here, it changes very rapidly. And then up in here, we're just assuming the bands are at 90, so that's half a bandwidth. So it all kind of wraps around the polar boss. Alright, so now let's do a load. Alright, I'm going to call this MEOP. I'm going to put a pressure. So we're going to highlight the pressure again. There's our pressure on the inside of the liner. Megapascals. Alright, so our job is basically ready to run now. We've got all of our materials, everything created. The next thing I'm going to do is create an output request. So layer numbers, I can just say all. The smoothing is just how when we sketch like the stresses along a layer, there's some spikes where one layer kind of goes over another layer. So we want to smooth that out a little bit. So I'm going to select E11, E22. I mean, I could select all of these if I want, but we'll keep it simple. Okay. So all we've done is we've created an output request, so when we're ready to post-process, we have it already. Alright, so what I'm going to do is run the job. Alright, let's see, I'll run 4 processors. It doesn't really matter on this, it runs so fast. Alright. So we have all these uvarm variables that, because we have all these orientations that are out of the plane, but we've transformed our material properties. See, if you look at these, these are our material directions. The blue is in the one direction and yellow in the two. Well, these these are not in the fiber direction, so we got to transform those global stresses into our fiber directions. So we do that with user subroutine. So we have all those stored, and a good way to view those is through our uvarm variables, but it's kind of confusing you have all these different uvarm things. So what we've done is, what I'm going to do is say fill results based on our extraction request. It's going to read all those uvarm variables and then put them in a form that's easy to manage. So now I'm going to double click on this. Here's the model names we have on our XML file. Here's the steps, COPVs, planes, so that like if we have 3D, we can cut it up into planes. And here's our output variables. So if we look at our wind angles, you'll see these go to 90 right up here. These are our helicals. These are our hoops at 90. Alright, and then let's say we do the plot our hoops and our geodesic helicals. Alright, so we've got easy access to all the stresses and strains along the base of each layer. Alright, so this thing is a very handy results manager, because let's say we have multiple steps and we want to look at the stresses, let's say before and after autofrottage, the strains and so on, and different MEOPs. We can very easily select different steps but the same output request and compare. So I'll do that in a different way. So let's say we have a design we want to change a little bit. We said, well, we want to add some stiffness or do something else to it. So what I'm going to do is I'm going to copy this model to demo 2. Okay, this is going to copy everything in Abaqus CA and then everything stored under our XML file into another model. Alright, so now we have demo 2 here, and we've got everything built, everything ready to go. But let's say we're going to say, well, I'm going to stiffen this thing up. Let's say I'm going to double the thickness on this last hoop, and let's see what happens. Okay, so now what I'm going to do, instead of going through and editing all these dialogues and resubmitting, I'm just going to say update, build, and run. Okay, so it's going through each of these steps that has not had a green check. So it's meshing it, it's going through the assembly, generating the material properties, generating the loading. Now it's running the job. And then as soon as it's done running the job, it'll look at the output requests, generate all the output curves, and store them on the XML file. See, now it's processing the first output request. Alright, that's completed. Alright, so both jobs are completed. Alright, so now we've got demo 1 and demo 2. So what I'm going to do is highlight it. Now what this dialog will do is it'll actually sort through, and when we have more than one thing highlighted, it'll show only those requests that both items have stored. So in this case, both models have MEOP instance names the same, the plane numbers, the variables are the same. So let's look at, let's say I'm going to sort this by hoop. So let's look at the first hoop and look at E11 and compare. So we see demo 2 has a much lower strain. So we can see it goes, from 0.66 to 0.58 or something. Right. So we've stiffened up that last hoop layer, so we have a big effect on the first hoop. Let's see what we have on the first helical. Alright, now the first helical, the strain, this is the strain in the fiber direction. Well, it's in the axial direction, it's not in the hoop direction. So it has a little bit of effect because the helical's not exactly in the axial direction. It's 10 degrees or 13 degrees off, so we can see it has some effect. But the point here is it makes it very easy to select all these different permutations of model names, steps, instance names, doing multiple tanks. We could do very quick comparisons of everything. All right, so what I've demoed here is really just a simple 2D model. It's about as simple as you can get. It's a symmetric model, axisymmetric, and the tank is symmetric. Now, the WoundSim, we have a support for shell models, 3D models. We can do 3D merged brick models, which is, let's say you have 100 layers and you want to do a car crash analysis. So you don't want to have 100 layers of brick models in there. So you can, let's say, merge 10 layers for a single brick and control the number of brick elements through the thickness. So we have all kinds of different capabilities for 3D. So I've just demoed 2D because it's very quick and simple to do that. All right, well, thank you very much for attending the demo, and if you have questions, please go to our website at customapps.com, and there's contact information there. Thanks again.